Good afternoon. Can you hear me? A little bit louder, maybe. Okay, so the last time we have discussed bonding, since we do this a while already, and we have discussed bonding in terms of molecular orbitals. So we have seen that we can have the atomic orbitals, they form new orbitals, a bonding molecular orbital and an anti-bonding molecular orbital. Because we can't lose orbitals. We start out, for example, hydrogen has a 1s1 electron, so the 1s1 orbital. Second hydrogen has the same configuration. Now they want to bond to each other. And of course, with Lewis dot structures, we know how to do that. But we have learned the linear combination of atomic orbitals. And the linear combination of atomic orbitals is they can overlap or interfere constructively, then they bond, or destructively, then they do not bond and they're anti-bonding. And the bonding molecular orbital is lower in energy than the individual atomic orbital energy. And the anti-bonding is higher than the individual atomic orbital energy. So we have, for example, and I just spoke about this here, we want to bond together two hydrogens to form H2. So each of them has a 1s1 electron. So now they constructively interfere, and with this they form bonds, and they form a sigma bond, which is lower than the individual energy of the atom, and they form an anti-bonding molecular orbital, a sigma star orbital. But in this case, the electrons, and we use the principle of Hund's rule, in this case we fill the lower orbitals first, and then we come to the higher orbital. And since we only have two electrons, both of them, and these molecular orbitals cannot have more than two electrons, just like every other orbital that we have discussed so far. So we have then here the two electrons in the sigma bonding molecular orbital, and this is how this looks like. There's density here where they bond together, and the antibonding has a node here, which means that it's higher. Structures with nodes are always higher energy than those without nodes, and you see that's the sigma antibonding, but there's nothing in there, so we don't use that. And then we have discussed the bond order. The bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. So 2 is the number of bonding electrons minus 0 number of antibonding electrons divided by 2 is 1. So the bond order is 1. Okay. Now, the next one in that same period, and the last one would be helium. So helium has a 1s2 configuration. The helium atom has a 1s2 configuration, and we take 2. So we form a bonding sigma molecular orbital and an antibonding sigma molecular orbital. But since we have 2 on each of the atomic orbitals, we have to put 1 in here, and 1 in there, and 1 in here, and 1 in there. So the bond order, so the bonding and the antibonding is filled, and the bond order with this is then 2 minus 2 is 0 divided by 2 is still 0. Okay? And so now this is filled. This has a bond order of 0. We're not going to lose these bonding and antibonding molecular orbitals. We just start filling up the next higher period. So we don't write those anymore, but they exist. So the next one would be this here, plus when we bind 2 lithium atoms together, Le2, that's in the second period, has a 2s1 configuration. So the same thing happens like here. One lithium has one here, but it's in 2s, and one lithium is here in the 2s. It forms the bonding 2s. The 2s form the bonding sigma molecular orbital. The antibonding is empty. With this, the bond order is what? What's the bond order? 1. Okay, good. All right. And then the next one in the period is still the beryllium. We want to bind 2 beryllium together. Beryllium has a 2s2 configuration, each of them. So we have to place 4 beryllium electrons, 2 from each beryllium atom. And with this, we put 2 in the bonding and 2 in the antibonding. And with this, the bond order is what? 0. Okay, it doesn't exist. When we come to the next period, where p orbitals exist, and we're already in the next period here, in the second period, there is bonding with p orbitals. So we can make sigma bonding p molecular orbitals, or pi orbitals as we call them then. And then we also have pi bonding. So sigma bonding molecular orbitals and pi bonding molecular orbitals. And this happens because we have 3 configurations in space. The p orbital can go like this, okay? This would be the py, this would be the px, this way, this direction here, okay? And so I fall flat on my face, that would be the px. And then you have the pz, that would be this direction, okay? Up, straight up. So when they interact in the next one you have to mention stands right next to me here. So we interact here, and this would be the internuclear axis, or the interatomic axis, because they are on the same axis here. All right? So they form a sigma bond molecular orbital. So with this, you have the py's forms the sigma bonding and the sigma antibonding, and the px and this px forms the pi bonding and the pi antibonding. And the x direction is given because it comes out of the px orbitals. And the same is true, of course, for the pz orbitals. You have the pi z or pi z bonding molecular orbital and the pi star z or pi z star antibonding molecular orbital. Okay? So there is the possibility now that you can have a double bond that way. And you will see that here when we look at the molecules. These are all homoatomic molecules, so they're of the same kind. So boron, carbon, nitrogen, diatomic molecules, oxygen, fluorine, and neon. And we can determine from the bond order number of bonding minus number of antibonding orbitals. So there's 2, 4, 6 bonding, minus 0 is still 6, divided by 2 is 3. Bond order is 3, that means you have 3 bonds there. Okay? We could very nicely explain the magnetism, for example, of oxygen, and I showed you an example where oxygen was paramagnetic and has magnetism, whereas we compared it to nitrogen. When we poured it through a magnet, the oxygen stuck between the magnet poles, and the nitrogen flew right through there, poured right through there, and you can see, this is no magnetism here. There are no unpaired electrons. And this was the last experiment, and then we have seen that oxygen had a color. Liquid oxygen was blue. And I asked you that question, which process involves a photon is responsible for the conversion of an O2 triplet, and I will explain this to you. A triplet is paramagnetic, to an O2 singlet is diamagnetic. Now, if something has color, what does it do? It absorbs light, okay? It emits it also, but first it absorbs it, and so that absorbed the light, the part of the visible spectrum to make it appear blue, and the answer was absorption. And you see this here, this is a triplet. They are not in the same orbital, in a different orbital. This is the triplet configuration, and the non-magnetic configuration would be this. So this electron flips in spin. So now I have this upspin and this downspin, and this is a higher energetic situation because it took up energy, and with this you have antiparallel spins. If they are not in the same orbital, then they have a higher energy, and the answer was absorption. I actually gave you the answer before I actually asked the question. So today we're going to talk about polyatomic molecules. That means, and not with the same kind of atoms, with different atoms binding together. And we need to think about this. So we said that we have a linear combination of the atomic orbitals. They form the bonding and the anti-bonding molecular orbital. And this looks different. It's a wave function, a linear combination, addition or subtraction, whatever you want. So if you look now, we have carbon. Carbon has 2 s's and two p orbitals. Okay, so we want to get a steric number. What would be the steric number of this here? The steric number would be 2, and the bond angle 180 degrees. And so this is called acetylene. And so how would we get a triple bond there? Where would the electrons come from? How would you be able to have a triple bond here on that carbon? Linear would be fine, but we don't know how to do a triple bond. Okay, that's the shortcoming. Now, it becomes even more difficult when we have a carbon has one partner here, and the partner here, and the partner here, there's an angle. So you probably can tell me what this angle is. 120. So that is the steric number would be then 3. And this would be, for example, graphite. Graphite is when you write with your pencil, you write on paper, and you put a layer of graphite down there, so there's no bonding between the layers. If there's bonding between the layers, then it becomes expensive, very expensive. That would be then something like this here. What would be the steric number? 4, and the angle would be 109.5 or 109, and this would be then a diamond structure. You have these structures, but they're interlinked with each other. And so this is very, very hard, and you cannot break them easily. So diamond is very, very desirable, and graphite is not so desirable. So never mind. I was just reminded in one of my early lectures, at one time I made a joke about this. We all would wear pencils as earrings, but that would be a lot. Actually, some people do, okay? so anyhow, so you see, how would you could accommodate something like this. You wiggle yourself a bond here, but two bonds like this, it is angle, is kind of difficult. So now how do we help ourselves with this? We look at our atom, and we have s orbitals and p orbitals on these atoms. That's carbon, all right? So these are wave functions. Why or who forbids us to use these wave functions and have them already combined to a hybrid wave function that will, at the atom, without any bonding, at the atom, that will accommodate that kind of geometry? And this is essentially hybridization. That's what happens. So the leisurely said, the atoms get ready for bonding. They ready themselves for the steric bonding in terms that they can accommodate the steric structures, the steric numbers that we need in these bonds. And so if you look, for example, if we have, so we combine these at the atom, put them in the right direction, they become a hybrid orbital, and then we can start bonding. All right. So if we combine an s and a p orbital, we get a hybrid orbital, and that hybrid orbital is called a sp hybrid orbital. So one s and one p orbital combined. So how many orbitals do we need to come out with? We have one and another one. We have two orbitals. So at the end, how many orbitals do we need to resolve if we do this hybridization? 1 or 2? Because yes, excellent, because we do not lose orbitals. And with this, we get two sp hybrid orbitals. They look like this here. This is the one of the positive, and this is the negative lobe, or vice versa, and the same here. And if you put them together, that's how they look. All right. And now we can accommodate all kinds of things. We have two sp orbitals. This will have a steric number of what? 2 will be a linear possibility, linear bonding, and a bond angle of 180 degrees. So now if you think a little bit more, I stop here. We want to accommodate a trigonal bonding. Trigonal bonding, how would you do this? You would have an 1s and 2 p orbitals. 1s and 2 p orbitals. How many hybrid orbitals would you get? 3. And they're called sp2 orbitals. That's that simple. That's all there is to it. These are sp2 orbitals, so they look like this here. There's one, there's the other one, and there's the third. There's the 3 sp2 orbitals, and now they're looking, if I put them together, that's sort of not that far apart from each other. That would be an sp2 orbital, and this would have the geometry of 120 degrees in between here, and the bond angle 120 degrees, and the steric number of 3. Okay, now what is the one where we have 4 bonding to 4 partners? What geometry would you need there? Tetrahedral. Remember, steric number is tetrahedral. So how do you get to? You need 4 orbitals, so you take 1s and 3 p orbitals. Then you get 4 orbitals, and they're called sp3. Let's do that. 1s and 1, 2, 3 p orbitals, and we get 4 orbitals, 1, 2, 3, 4, and that's how they look. With this, we get a steric number of 4, and a bond angle of 109 degrees. Okay, so the atoms is ready for bonding. Now we can bond here, we can bond here, we can bond here, we can bond here. That would be, for example, carbon in diamond, for example. Okay, so in summary, I'd like to say this. If you have a linear hybridization, you need a linear molecule, you do an sp hybridization. If you have a planar molecule, trigonal planar, you need an sp2 hybridization. And if you have a tetrahedral coordination, steric number 4, you need an sp3 hybridization. Okay, you take 1 s and 3 p's. So obviously, if you have s and p's, there's no p left then. Okay, and we get the hang of this when we practice a little bit. Oh, let's do this right away here. Okay, so benzene, you remember, benzene has this, what was the number? The bond order, was it bond order? It was a fractional bond order. Okay, remember anybody what the bond order was? There was this mesomeric structure, or this resonance structure. So the bond order was what? 1.5, because you had one single bond between the carbons, and then you had, each of them had one electron that you had to, that's a 6, that gives you 3 bonds that you had divide by the 6 partners, okay? So that was the bond order 1.5, but I'm not asking about this. I'm asking about this, this, and this, and this, and this, and that carbon atom. So the bonding to this, this, and that. What is this here, the white stuff? Hydrogen, okay. So what is the hybridization in the carbon orbitals in C6H6? Is it SP, SP2, or SP3? I'm a little in time pressure, so I give you 1 minute. You should probably, you either have it in 10 seconds or you don't. Fun? No, benzene is not a fuel. Benzene, because a lot of organic chemists using it. It's highly, highly carcinogenic. I used to clean my windows on my car when I was young with it, without gloves, but my hands are okay. Benzene is a very common solvent in organic chemistry. It's obviously not highly carcinogenic because my hands are still okay. I did this a lot in the winter to get the grease off my windshield. It is, but if you bathe in it, it's probably carcinogenic. It is. You want to avoid contact. But that's 40 years ago. Benzene is gasoline. Okay. Okay, let's see if I get a heart attack. No, excellent. See, good. All right. So that was an easy one, and the whole thing is easy. So we have here one hydrogen, one carbon, that's the central carbon, to the next carbon, to the next carbon, to the hydrogen, and the same thing goes along here, along the ring. So the bond angle is 120 degrees, and sp2 hybridization, and this was the answer. So this is the other carbon, here's the central carbon, the other carbon, and the same thing starts here again till we have the ring. Okay, this is an sp2, because that carbon is also sp2. Yeah. So, and this is an sp2, this is sp2, the carbon, and this is just the s from the hydrogen. Okay, this is an sp2s, so the answer was sp2. Now, let's think about ethylene. Ethylene was, I had this here, ethylene, wasn't that ethylene? Where is it? Ethylene was in the previous picture. No, previous picture. with you. Did I have ethylene here? No, I had it somewhere here. Anyhow, that has a double bond. Okay, ethylene has a double bond, carbon double bond, 2 H's and 2 carbons. All right. Okay, if you don't have discussion section, I skip that. Okay, all right. So we have carbon. There's one. We have available 1, 2, 3, 4 electrons. We have 4 electrons available. And now we want to have a ethylene would have 2 hydrogens on each carbon, 2 hydrogens on each carbon, and then a bond to the next carbon, and again 2 hydrogens. So what kind of geometry would you need there? Trigonoplanar, and this would be hybridization, would be sp2. You use 1 s and 2 p's, so each of them has 1 electron in there. How many electrons do you have left? You have 4. How many you have left? 1 you have left. And this is the unhybridized p orbital. So you hybridize this, and this forms a bond here. There's one here, and one here. It forms the bond, okay? And here it would form the bond with the hydrogen. Here it would be a 1s, sp. That would be a sigma bond here, okay? And of course, I forget about the anti-bonding now, all right? We just skip that because it becomes too complex, all right? But there is anti-bonding. Just if you know what the bonding is good enough. Yeah? And this will do the trick. So this would be a sigma bond, but now this here, and this here, and this here is the sp. What is it? sp2, okay? But you have one p orbital here. You see that? That's the p orbital. So now this stands head to head and toe to toe. What kind of bond can you form? You can form a pi bond. Exactly. You learned it before the last lecture. And you form a pi bond. So that forms the sp2 forms the sigma bond, and this here, the overlapping in phase, forms the pi bond. The p set forms the pi star. We only look at the bonding, not at the anti-bonding and this kind of stuff. It gets too complex. All right. So is that clear? You with me? Yes. Okay, three got it. Excellent. Okay, there's the molecular structure. This was the sigma bond here, but there's one bond missing. This is the sp2 from this here and this here, and now we need the double bond. This would be an sp2s. The s comes from the hydrogen, so it bonds here. There's one in the hydrogen and one in the sp2. Makes the bond here, and now comes the kicker. This is the p set that forms you here your pi bond. Okay, so that's which one is stronger, sigma or pi? Sigma is the stronger. Okay, sigma. Yeah, sigma is stronger. So I said the double bond is not quite double than the single bond, and the triple bond is not quite 3 times the single bond, okay? Because the 2 pi bonds you have in there. So if one is a sigma, and if you have one double bond, must be a pi, and the second double bond must be also a pi. We get to this a little bit later. So now let's look at this bond here, okay? So I want to know from you what atomic orbitals make up the bonding molecular orbitals shown here. So this one, what would that maybe made up? Would it an sp on the carbon, and an sp on the oxygen, or a pz on the carbon, and pz on the oxygen, or an sp2 on the carbon, and sp3 on the oxygen? What don't you think about this? Show me what you got. There's one more in here. That's a pretty good result if C is right. So this is 34, 36%. That's a little. You think C is right? You're sure about that? Okay. Why don't you discuss this with each other? Thank you. Okay, steadfast. Excellent. Good. So you don't need much explanation here. This is, you got it right, yeah? Okay. This is 1, 2, 3 neighbors here. This is what counts as a single bond. So this is the sp, what is that? sp2. That's a 120-degree bond angle here, okay? That's the sp2, that can be this here. And there's only one sp2. So this must be 1, 2, 3, 4. That's tetrahedral here, isn't it? Okay, that's sp3, tetrahedral at least for electron geometry. You know the difference between electron and molecular geometry? One counts all the electrons, and the other one